All right, in this video, I'm going to solve a few of these exercises here using the definitions of big theta. And so let's begin. So I want to start with the first one here. Okay, so working with this function f of n, we now want to find upper and lower bounds, or again, another way of saying that would be to apply the definition of big O and big omega. And remember and recall that those two definitions together, the upper and lower bound together, the big O and the big omega together, establish the theta bound that we want to prove. And that is what we're looking to prove here, is a theta bound. And so what we're looking here is theta of, and a good guess here, and established in the exercise, is we want to show that this is in theta of n cubed. And if it's been a while since you reviewed your big omega or your big O, usually for a polynomial we're going to look at for the highest degree term. And so in this case we're dealing with a cubic polynomial, so we expect this to be in theta of n cubed. So hopefully without too much trouble we can prove this relationship. And usually we're going to split this into two, the upper and the lower bound. And occasionally one is easier than the other. But I'm just going to go ahead and I'm going to look for an upper bound first. Often upper bounds are the bounds we look for first. So let's go ahead and do that. 6n cubed plus 3n squared minus 14n plus 2. And we want to show that's less than or equal to something. So recall that what we might be going for in the end is we might want to show that this is less than or equal to b times n cubed for some value of b that we get to pick. But of course, that means we need to fill in the details. Now, one thing in this example that might stand out or might be important for us to recognize here is that this term is negative. Again, assuming our n is positive. For our problems, we're always assuming we're in the realm where n is positive, so that would make this term negative, which because of this minus sign here. So with a negative term, we'll notice that the rest of the terms, all the positive terms together, the 6n cubed plus the 3n squared plus 2, all of them together are made smaller by this extra term. The minus 14n makes the whole thing smaller. So what that means is that this stage of the approximation, as we're going for an upper bound, since this term makes it smaller, we can drop it off. If we drop it off, if we ignore the minus 14n, the whole thing gets bigger. And that's what we're going to do with our next step in the approximation. So we're going to say that this is less than or equal to 6n cubed plus our 3n squared plus our 2, but we're going to leave out that minus 14n. Once again, that's just another approximation tool in our toolkit. And we want to build up a small collection of tools that we can use for approximating as we go. We're going to use them more and more often. We're not there yet. Remember, what we want this to be at the end, we want to look for something that's going to be like less than or equal to b times n cubed. And so far we still have an n squared term and a constant term, and we might want to do something with them. So here we're going to look back at our toolkit for approximation, and we're going to remember another toolkit or another tool in our kit, which is as long as we're in the realm where n is positive, which again we are, then that means we can multiply terms by n, and that will make that term bigger. Now, as long as it's a positive term, like the ones that we are here, our plus 3n squared, for instance, or our plus 2, multiplying them by n would make those terms larger, and since they're positive, it would make the whole thing larger. And that's what we're trying to do, get an upper bound, so we're allowed to use tools that make the whole thing larger. So let's go ahead and multiply some of our terms. Now, we don't want to mess with the first term. The 6n cubed is already an n cubed term. It already matches the pattern that we're looking for. So I'm going to multiply 3n squared by n. So I'm going to continue down here. This is less than or equal to 6n cubed, and then plus our 3n cubed as well. And then plus, I'm going to multiply my 2 actually by n 3 times to get me another n cubed. So I'm going to get 2n cubed. So in total, adding these together, what do we have here? 6 plus 3 plus 2, that's 11 n cubed. So what we've now found here is a good candidate for the value we need to pick here. Maybe I'll write it over here. I'll say, why don't we set b be 11? And actually, for this particular approximation, we haven't done anything except assume in each of our approximation steps that n was positive, which we already know is true. So this means that this works for any n greater than or equal to 1. So we'll keep that in mind as we continue. And as we continue here, the next thing we want to do, we've established an upper bound, is now establish a lower bound. Working with the original f of n here, we now want to find a lower bound. We found an upper bound, and we want to find a lower bound. Now again, lower bounds can be kind of easy. Remember, we can say the whole thing is probably greater than, for instance, 0 is usually a good guess. We have a negative term in there, so we might want to be careful there. But finding some lower bound might be something we could find pretty easily. What's maybe a little trickier is we want to find a tight lower bound. That is, on the lower end, we might want to match. We want to match up the degree, at least in the case of polynomials, with the upper bound. And if we do, then this gives us what we call a tight bound. And that's what we need to establish our claim of a theta of n cubed here, is we need a tight bound, both an upper and lower bound, a big O and a big omega, that match or match one another. So since we're looking for a lower bound now, we should be clear we were in the realm of greater than or equal to. And maybe this is a good time to point out or remind ourselves that when we're doing approximations, once we've picked the direction, once we've picked the sign, we have to stick with that sign. We can't turn it around now on the next one. We can't say this is greater than this is greater than this, and then this is less than. If you do that, you can prove anything, and while that might be useful, it's not good math, so we're not going to do that. So now we're on the lower bound. We can only use greater than or equal to tools in our toolkit. We can't switch that around. All right, so one of the things that stands out right away is we were able to drop off the negative term when we were looking for the upper bound because it only made things smaller. We're not allowed to do that on the lower bound. Making it smaller is what we want to do. So what we're going to do instead is we're going to look here and say, oh, these terms, the positive term, the plus 3n, and then my plus 2 here, those things only make us bigger. The 6n cubed minus 14n gets made bigger by these two terms, so we can actually drop them off. So the first step that we're going to do here, say, okay, let's drop them off. We're still going to have our 6n cubed, and we can't get rid of our minus 14n, so that sticks around, but we'll drop off the other two terms. Okay, that makes things a little bit easier to work with, but we still have to deal with this. What we actually want to show is that this is greater than or equal to a times n, or more, sorry, a times n cubed, again, to match our upper bound. So if we wish to do this, then we're kind of on the right track. We have 6n cubed, that looks like an a. But this minus term is what's causing us to have a little extra problem here. If this was a plus term, we would have dropped it off like the other two, and we would just say, hey, a equals 6 works. Now, the term down here, this minus term happens to be, it doesn't match. It's not an n cubed term. It's a linear term, n to the power 1. It's a lesser term, which is usually what it is. Otherwise, we've done our approximation wrong at this point. We always want to focus on the greater term. And so since it's a lesser term, what that means is when we get to large values of n, the contribution it makes is insignificant compared to the n cubed. And in fact, it should probably not minus off very much. And so we might look at it and we might say, okay, at this point we have a couple options. We might go ahead and make a guess at what value of A might work. Now I don't want to go there right away. At first I might try one of my other tools because some of our tools, even though we used them on the upper bound before, might also still work on the lower bound. And here's one example I might show you. Say we multiplied here by another n. Now remember, n is positive. It's greater than or equal to 1. So multiplying that will make this term bigger. But because it's a minus term, that means it makes the thing we're minusing off bigger. Okay, we make the thing we're minusing off bigger, which makes the whole thing smaller. Okay, which is what we want to do. So that's something we're allowed to do. We could do that. So we could promote this to n cubed. The only problem is then we would get 6n cubed minus 14n cubed would lead us to minus 8n cubed. And remember, one key about A is it must be positive. We can't say minus 8n cubed. So even though that's a great tool, it's a tool that does too much work. It's what we might say it over approximates. Okay, and that's the risk with the approximation. We have a lot more tools we can pick from, but we're at risk of over approximating, maybe giving away too much. Okay, so we don't want to do that. So maybe it's a good point. Let's go ahead here and let's say, well, I'm going to guess. I'm going to say I think this is probably greater than or equal to 5n cubed. Now why is that? Well, 6n cubed minus off something that is probably, as n gets large, pretty insignificant. The minus 14n is going to be pretty small. And at some point, it's probably going to be less than 1n cubed. Okay, it's going to be less than 1n cubed at some point. Now, there's a little algebra we can do here to make this very clear. So I want to make this very clear. We're going to have 6n cubed minus 14n. And we're saying this is greater than or equal to 5n cubed. Now I'm going to go ahead and transfer things around a little. I'm going to move my minus. I'm going to do minus 5n cubed on each side. So that's going to leave me on the left-hand side. I'm going to have an n cubed. Then I'm going to do plus 14n on each side. I have. All right. So we now have n cubed is greater than or equal to 14n. All right. I'm going to go ahead and cancel out. And we're going to write n squared now must be greater than or equal to 14. Well, taking the square root of both sides tell us then that n must be greater than or equal to root 14. All right. Okay, we could go maybe a little bit further and say, well, what's root 14? And before you go reaching for your calculator, which of course is maybe our instinct, or of course Google will probably tell us right now if we go type that into Google. Let's see if we can do that without some technology. Let's see if we can approximate that. We are talking about approximation here, so maybe we don't need to know exactly what this number is. We want to know about what this number is. Well, what are some perfect squares nearby that we know? 16 is 4 squared, 9 is 3 squared. So our value, the root 14, we can quite easily approximate is probably between those two, 3 point something. And since, remember, we're going to be picking here a value of nf that we want to use in our final proof that the definition holds, we want to know at some integer value for which this works. So we could pick our nf in this case to be 4. And that would be sufficient for us to know that this holds. So let's maybe just complete our what our proof would be. Here in this part of the proof, we picked our a to be 5. And then with a little bit of side calculation here, we figured out that we should probably pick an nf equal to at least 4 was our guess here, or our choice. 4 being greater than the square root of 14. Now remember, on the first proof, our upper bound, we also need to pick an NF. And in that case, we said it worked for all positive n. So since the upper bound works for all n that are positive, the lower bound is more restrictive. It says, no, it only works if we're greater than or equal to 4. I'm going to pick the maximum of those two, NF equals 4. So these will be the values that we would use in our final proof. All right, so looking at this one, again, the question asks us to show that this is in theta of, and maybe we should make a good guess here. We can see that if we expanded this, the highest degree should be 12. And so that's the guess that I'm gonna put here. Again, we're going to try and do upper and lower bounds, but maybe it's going to be worthwhile for us to simplify this before we do that. Now, again, we probably have a little bit of instinct tied to a lot of the algebra that we've done up till this point, where we've dealt with equations, algebraic equations, where again the left-hand side must be equal to the right-hand side, and so on. In such cases, the rules that we can use are very specific, and so we might have an instinct here of what we should do here. We should expand the exponent. That's the rule that our algebraic teaching would tell us. Now, one reason why I've included this example is so we can see that maybe those first instincts, those first algebraic instincts, aren't always the best instincts if what we're looking for is the quickest solution here, the quickest way to our upper and lower bound. And I'm going to start here then. Again, why might we not want to do this? Well, expanding this to the 6th power is going to require a lot of multiplication. This is a trinomial. We're going to end up with a lot of terms. We don't want to make an error in that. So is there some way that we can do this a little bit quicker and easier? So again, I'm going to start here with the upper bound, and I'm going to use the same rules as before, so I'm going to go a little bit quicker. All right, so I am going to start with the upper bound. So here for the upper bound, we want to be less than or equal to. And again, for the upper bound, again, let's remind ourselves which term can we drop out here. This minus only makes things smaller, so if we got rid of it, the whole thing would get bigger. So let's do that. We'll get 2n squared plus 3 all to the power of 6. So now this is made greater, and now we could again follow our instincts, expand out the exponent, and we've actually simplified things by eliminating that term. But if we've now got a little bit of experience with our approximation, we might say, hey, wait, we can continue this. We could say we already learned another rule, 2n squared. We could probably promote that guy, the next term, to also an n squared, 3n squared. Okay, get that all to the power of 6. We still haven't had to expand that exponent, which is great. All right. But I might continue here. Let's just group what we got inside there. Looks like we had 5n squared all to the power 6. And we could go maybe one further. That's going to give us 5 to the 6th times n to the 12, and n to the 12 was the value that we had up here. So we've got the right value, and then we've also got a good value here for our b. So again, maybe over on the side here we could say maybe b is equal to 5 to the power 6, which of course we could go and punch in our calculator if we don't know what that is, and I offhand don't know what that is. So let's consider that's our upper bound. Oh, and maybe now that I notice, I'll maybe make a comment. You'll notice I've used a kind of notation here. This is a notation that I favor, especially when teaching, is whenever I use one of my tools from the approximation toolbox. So here we dropped out the minus 4n, which is only going to be true. Some of the times that's going to be a true less than, other times it might be equal, but when we did that, since it was an approximation, I have to use the less than or equal to sign. And it is somewhat convention. Once you've used it, every transformation you do, you always use that same one. Well, here I've changed to equals. And the reason I've done equals here is it's a signal to my reader, you, my viewer, that this transformation here follows actual algebraic rules. So this is just a straightforward algebraic transformation. All I did was lump these two terms together, right? Same thing in this next step. All I did was apply the exponent 6 to the single term inside. Once I eliminated the trinomial and the binomial, that made it a lot easier. So we land at these last two steps algebraically, even though we did some approximation ahead of time. So I'm going to continue that in my videos, that notation, that when I do an approximation step, I'm going to try and use less than or equal to or greater than equal to. And then when I do an algebraic step, I'll use the equal to, just to make it easier for a viewer or reader to follow along. But now we're going to do the lower bound. So we're going to do greater than or equal to. Again, if we want to maybe start out using that same rule, we could say 2n squared plus, we're going to drop out the plus. So we'll drop out that one, but we won't be able to drop out the minus 4n. Again, our instinct might be to expand out the binomial, and again, if we can't find another step here, that might be the appropriate next step. Well, notice we also can't promote that inner step, that inner value to n squared without making our constant out front negative again, and that's something that's not permitted. So we might want to make a guess. Again, we might want to go ahead and make a guess. So I might say, well, this might be greater than or equal to. What might I think it's greater than or equal to? That's where the guess comes in. Guess is sort of one of the final last tools in the toolbox. If none of your other tools are going to work, well, you can just guess. You can just guess what it's greater than or equal to, and then check afterwards to make sure that it's actually true. What might we guess? Again, notice that 2 won't work. The minus 4n makes sure that we're smaller than 2n squared. But maybe just n squared, which would be a total of n to the 12th. So in this case, if we bet that if we can make this work, then we've got a case where our a would just be a 1. So again, let's write this down. We only have to worry about the stuff on the inside. If we take the 6th root of both of these, we've got the same thing. So I only need to worry about the inside. So I've got my 2n squared minus 4n must be greater than or equal to n squared. Again, with a little algebra, we'll take the n squared, throw it on the other side. That will give us only 1n squared after minusing off both sides. We're going to bring the minus 4n on the other end. So we've got greater than or equal to 4n. Here, maybe it's not too hard for us to see, after we cancel out one of our n's, that our n must be greater than or equal to 4 again. All right, that's good. Okay, that worked on our last one too. And hey, that worked. That was a good guess. That worked for a equals 1. So here we'll pick our n sub f is 4 again. Again, our up at the top here, all these approximations worked for no matter our value of n. And then for our final one here, our calculation of a, we saw here that we had to make a guess, and then making that guess, we had a little bit calculation for which values of n's that would work for, and sure enough, we found out that would work for n greater than or equal to 4. Okay, so now let's continue with our next problem here. And again, maybe I'll just copy it down to start out. Okay, now the key here is this is a log. I haven't stated the base of the log, but we should assume when we're dealing with computer scientists that they mean log base 2 if they haven't told us otherwise. And maybe I'll put a little cheat sheet over here, something for us to remember. You may have seen this before, the natural logarithm, or log base e, where e is Euler's number. Well, computer scientists will sometimes use a different shorthand, L sub g, and that just means log base 2. You may see me slip into that shorthand every once in a while in my notes here, and if so, all I mean is log base 2, which is the standard log for computer scientists. So here we've got log base 2 of our this polynomial function here, quadratic function. And what do we want to show? Well, again, we've got a question asking us to show that this is in theta of log n. And this is something we might want to build with our intuition to start out, that the log class includes a lot of functions, and even though we've gone ahead and taken the n out of there and replaced it with a quadratic, we're still in theta of log n, and that's something, well, we're being asked to prove here, so let's see if we can show that. The upper bound here is going to probably be the more critical one, but let's start again, well, let's start with the upper bound. So we want to show what this is less than or equal to. We're looking for some b times log n. So one thing we want to do is get rid of the stuff that's on the inside. Okay, we want to show, again, some of the tools that we used before will still work. You'll notice now, because this is a log and not an exponent, we don't have the option of expanding this trinomial out. It's not a trinomial raised to an exponent. We've stuffed it inside a log function, and so that makes it a little bit harder to work with. There are algebraic rules how to work with things in a log, but I don't really know of any to help me with this. Maybe I could factor this or something. There are a couple tricks we could use, but at the moment I don't see any. Luckily for my approximation tool belt, we have a lot more tools in that one, and I have a few in mind that I could probably start by using. The first one I notice is, hey, I want to make this whole thing bigger. How can I make it bigger? Well, why not get rid of the minus term? Now, this is a little bit, has a little subtlety in it that we need to also raise. This works primarily because log is an increasing function or non-decreasing. And so if we decrease its argument, we would decrease its value. So removing it, that decrement in its argument, we make the whole value larger. So we will go ahead and register that. We're going to do that. We're going to get log base 2 of 3n squared. We've dropped off the minus 5, so we'll still have the plus n. Okay. So continuing then, again, using one of our tools before, we can make our n larger. So we can say that this is less than or equal to log base 2. We had already our 3n squared, and we'll just promote this one by multiplying it by an n. We'll make it larger and make it n squared. So the whole thing then is log base 2 of 4n squared. We can finish this off in a couple of ways. There's some algebraic rules that we can apply here to transform this. This is a product, the 4 and the n squared. The other thing we can see is it's actually 2n times 2n. We could factor it that way if we wanted, and get two terms there, 2 times log of 2n. But why don't we just split it out, and maybe the more straightforward way is going to give us log of 4 plus log of n squared. Again, log of 4, log base 2 of 4, well, that's just 2. And then we're left here with log of n squared, which we can again apply the log rule to give us 2 log n. Remember, an exponent on the inside there we can bring out front as an argument out front. So we get a 2 out of this one. We get a log n squared out of this one. Now, maybe I'll do the last couple steps a little bit quick, but this is going to be 2 log n plus 2 log n. And then again, I'm going to say, well, that's equal to 4 log n. So, oops, I've gone ahead and done it. Switch the order of my sign. That's not something we're allowed to do. But that was an error in writing. That was not an error in our calculation, the logic we were applying here. I just miswrote that. So that should be this here. Again, this is going to be in, here we're just applying straightforward algebra, and that's going to arrive us at a value of 4 log n. So for keeping track over here, we might say b equals 4 is our choice for one of our values. So this log of this quadratic polynomial here, after some approximations, making it a little easier on ourselves, we never had to calculate what it was actually equal to. We can see that that's less than or equal to 4 log n. And maybe an interesting thing there is 4 log n, if we bring that 4 back in using that same rule we just applied, that's log of n to the 4th. So we've sort of over-approximated this polynomial here by saying, hey, well, that's greater than n to the 4th. Okay. Again, this should work for all of our positive n's that we're concerned with, so we should be okay here. Let's continue on. Maybe I'll make a little more space for us here. So now we're going to continue with the lower bound. Here, well, we dropped out the minus 5, which made us smaller up above, so we can probably drop out the plus n here to make us smaller on the lower bound. Log again of 3n squared minus 5. Again, unfortunately, we can't promote our 5 to an n squared and just make it smaller in that way. So we might want to make a guess here. So I might say this might be greater than or equal to log of, I don't know, 2n squared. Now here, I make this choice of 2n squared just because 2 is less than 3. The 5, and when n gets large, this minus 5 probably isn't going to mean very much to us. But then I think I might go back to the calculations I just did. Having that value in there, that 4, ended up giving me a constant out front, which I had to do more approximation later. So maybe it will be better for us up front here. Say, hey, that 2 is good, but a 1's better. A 1's going to work out better for me. Is it still true? Yeah. This is probably bigger than 1 n squared. Okay. So let's keep going there. That means we need to, again, solve this little bit of final bit of approximation. We want to know when 3n squared minus 5 is, what, greater than or equal to just 1n squared. Okay, now this time when we do it, we're going to end up with 2n squared is greater than or equal to 5. Again, if we want to be exactly precise here, then that means that our n squared must be greater than or equal to 5 over 2, or that n must be greater than or equal to the square root of 5 over 2. Okay, that's pretty precise. We've gone ahead and done that. But notice here, I could have just said, look, if here we're saying that 2n squared must be greater than or equal to 5. Well, if 1n squared was greater than or equal to 5, that would be good enough. And that would leave me with n is greater than or equal to root 5. And then beyond that, we could even say, hey, if n squared is needs to be greater than or equal to 5. Well, if n was greater than or equal to 5, then n squared would be greater than or equal to 5. So we might be able to go even a little further. And both of those steps just make it a little easier to calculate than having to figure out what the square root of 5 over 2 is. So to make that clear here, we could go ahead and choose our a equals to be 1 here, and our nf, we could just pick 5 if we wanted, and that would work. Okay, so maybe we should go on to our last, the last one I'm going to do is this last one. It's sort of a challenge problem. And then I'm just going to consider the last two, which again are sort of challenge problems to make us think, but aren't going to immediately apply the techniques that we're learning. The first one is, it says show that for any two functions, f of n and g of n, here it says f of n and g of n, sorry, are both in big O of n, that f of n plus g of n must be in big O of n. So to do that, we are going to rely directly on the definitions. And so I'm going to remind ourselves then that if f of n is in big O of n, then that means f of n is less than or equal to b times n for n greater than nf. Then, so that's what we learn from the definition of what f of n being in big O of n is. We know that. We can apply that rule and we can say the same thing will be true, that if g of n is in big O of n, then g of n is less than or equal to, and I'm going to pick a different term here. I'm going to say c times n for, and again, I'm going to call it a different value, n is greater than ng, for our new function g. So here we've got these two constants that we know are true. So let's go ahead and see, well, what is f of n plus g of n? That could be less than or equal to, now applying my rule that we have above here, f of n is less than or equal to b times n. My g of n is less than or equal to c times n. So the two of them together, adding them together, must be less than or equal to b n plus cn, which of course we can see is just equal to b plus c all times n. And that, since b is a positive constant and c is a positive constant, b plus c must be a positive constant. So we can conclude that f of n plus g of n is also in big O of n. Again, that concludes a proof, which now becomes a tool that we can use. It helps build our intuition that for any two functions in, say, this class big O of n, that if we add them together, we remain in that class big O of n. We don't somehow get better. And that's a truth that is also true for actually a whole bunch of other classes. If we take two and we add them together, we stay in that class. But might not be true if we multiply the two functions or do another operation. So I want you to consider that. You might think of other little proofs you can make for your own little theorems that, again, will build your intuition and maybe help you think about these problems as you go forward. Okay, I just want to finish this video with this final problem here, talking about this function n to the power of sine n. And maybe to do this, instead of actually proving it, what I'm going to try and do is just help us think about the problem. So to do that, I've drawn sort of this simple axis here. I'm going to think about the two functions that we've created. So one of those functions is this function, which we could say is n. Now, why did I say two functions? Well, let's think about this for a second. Our sine function, if we remember, does something like this. Now, it does this along the zero. It oscillates up above and below. We can remind ourselves that it actually oscillates between positive and -1. So the highest value that it gets to is +1, and the lowest value it gets to is -1. So when we think about this function n to the sine n, the highest it's ever going to get when that sine value reaches 1, our function is going to come up and approach this line I've just drawn here. Now the other line we can draw, this one might be a little bit harder for me, is something like this. Yeah, there we go. This is about 1 over n, or n to the minus 1. So this value is also the lower bound as our function continues on. As the sine function comes down to the 0, we're going to come down to that function here. Now, let's see if I can remember this. What happens over here, I'm not too concerned with. But once it gets over here, we're going to start doing this kind of pattern, where our function n to the sine n is going to oscillate between these 2 points. So one of the reasons why I'm interested in this function, and why we might be interested in it as well, is that we can show that, say, after this point here, I just picked it arbitrarily, that could be our n sub f if we like. After this point, it's actually easy to show that n to the sine n is in big O of n. So that's the question we had up above there. Show that n to the sine n is big O of n. This picture I've drawn kind of shows it. We're showing that the function is below the line. So the value b that I've actually chosen here is just 1, because I've just drawn the line there. So again, it's pretty easy to show. But the second question we've asked there is sine of n in theta of n. To do that, we would need to show the omega side as well. And these deep dips that it's doing, dipping down to this n minus 1, this prevents us from proving an omega bound. And as a result, this weird function that we've defined here, n to the sine n, is not a great candidate function for a runtime function, first of all. And it has no theta that we can prove in a standard, using a standard runtime function like a standard polynomial. So it's a bizarre operating function. There might be some more mathematical things we could do with it, but for the purposes of an analysis of algorithms, this function is not representative of the runtime of any algorithm, and so it's merely brought on for interest's sake. All right, that will be the end of this video, and in the next video I would like to present the little o notation, the limit test, and then practice with that a little bit. All right, thank you, and we'll see you in the next video.